Today we're going to discuss a lesson that actually isn't in your textbook, but is a lesson that I've taught at this point in the past, and I believe it's helpful for understanding the whole process. And it's entitled Tangents, Velocities, and Other Related Rates of Change. So, we're going to talk about two ways to find the equation of a tangent line. It's been tricky so far because to get slope, you need 2 points. But now that we know limits, you don't need both those points. So, here's our first way of finding a tangent line. It says the tangent to a curve, y equals f of x at any point P, A, f of A, is the line through P with a slope of, so our formula, now keep in mind, this works great at 1 point. If I throw a different point at you, you're going to have to do the entire process again, where our next method, definition 1, and then the next one is called definition 2, is going to give you a way to come up with an equation that can find you the slope of a tangent line anywhere. So, let's start with an example. It says find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. So, our point's 1, 1. We need 2 points to find slope. So just like we did a few sections ago, we come up with a generic point at x, technically y, but in this case y is x squared, so we use x squared. And the limit, as x approaches a, which a is our x value of our point, of the slope of these two lines. Now, right away, you can tell that you can't plug in that 1. So, we need to do some algebra. The limit, as x approaches 1, of x plus 1, x minus 1, all over x minus 1, is the same as the limit as x approaches 1 of x plus 1, so we get 1 plus 1, which equals 2. Now, what we were finding this whole time, this is the equation for the slope. So now that I have the slope, I can use point slope form, put in my slope, my x and my y were 1, 1, and find that y equals 2x minus 1 for the equation of our tangent line. That's definition 1. Now definition 2 is a little bit different. This time it involves the difference quotient, and it will come up with an equation for finding slope at any point on a curve. So if you need multiple slopes, this is the route to go. And it is the difference quotient with the limit as h approaches 0. So let's try one of those. It says find the slopes of the tangent lines to the graph of the function f of x equals radical x at the points 1, 1, 4, 2, and 9, 3. We're finding 3. The process we just did will only find it at 1 point. I doubt you want to do that process all 3 times when method 2 will allow us to do it once and apply it in several situations. So, f of a plus h all over h, and f of x is radical x, which is why we run into this situation. We need to plug in the 0, which we can't, so we are going to have to rationalize our numerator, which we have done before, and we get the limit as h approaches 0 in the denominator. Just leave it. Don't bother spoiling. And in the numerator, we get a plus h minus a. Those a's cancel out, which then allows us to cancel out the h's. And then we have the limit as h approaches 0 of 1 over radical a plus h plus radical a, which when we plug in 0 for h, we get 1 over radical a plus radical a, or 1 over 2 radical a. And that is our slope, our equation for slope. So, if I talk about the point 1, 1, which is the first one they asked for, our a value is 1, so slope is going to be 1 over 1/2. Our next point was 4/2. So slope is going to be 1/2 radical 4, again our A value, or 1/2 times 2, or 1/4. And finally, at 9/3, slope's going to be 1/2 radical 9, which is equal to 1/2 times 3, which is 1/6. So now from that one equation for slope, right here, we can find the slope at any point on that curve. So at an infinite number of points, we can find the slope. But that's definition 2. Definition 2 is going to be the one that you want to make sure you completely understand, because it's not going away. It's going to be the one that sticks around while definition 1 fades out slowly, and that's okay. Velocities, functions will always be position functions with respect to time. Average velocity, simple way to remember this, average velocity is slope between the endpoints. It's a good way to think about it. So it's the slope between the endpoints, where instantaneous velocity is that definition 2 that we just learned. The limit as h approaches 0 of the difference quotient. Technically, definition 1 would give us instantaneous velocity also, but rarely do you want the velocity just at one point. Oftentimes you want an equation for velocity, which is why we use definition 2. So, it asks for, suppose a ball is dropped from 450 meters above the ground, where the distance the ball traveled is measured by the function s of t equals 4.9 t squared, and t is measured in seconds. So let's find the average velocity. When you see average, think slope, and make sure that sticks, because when we get to reviewing for the AP test at the end of the year, you're going to be mad that you don't remember that. So what we need is our point at 1 and 4, and then we're going to find slope. So if we plug 1 into 4.9 t squared, we get 4.9. If we plug 4 into 4.9 t squared, we get 78.4. So our average velocity will be that 78.4 minus the 4.9 all over the 4 minus 1, which works out to be 73.5 over 3, or 24.5. Now for the label, our y value is measured in meters, and that's what's on top, so it's meters. And our x value, 1 and 4, is seconds, so it's meters per second. Instantaneous velocity is a little different, remember? It's going to be the limit as h approaches 0 of our difference quotient. Our difference quotient is f of a plus h, so 4.9 a plus h squared, minus f of a, 4.9 a squared, divided by h. Now if I do a little math here, we get, I'm going to simplify this all at once, we end up with 4.9 a squared plus 9.8 ah plus 4.9 h squared minus 4.9 a squared, and from here our 4.9 a squareds cancel out. We still have our h in the denominator. With that h still in the denominator, we can factor an h out of the top. Divide by h. So our formula for slope, when we plug 0 in for h, is 9.8a. Because, let me fix this. I left my a out of here, 9.8a plus 4.9h when we pull out an h, which leaves us with 9.8a. And this is our equation for slope. So if we want it at 5, for velocity, actually is what we're finding. So the velocity at 5 is going to be 9.8 times 5, which is equal to 49 meters per second. Now, the next part asks, how fast is the ball traveling when the ball hits the ground? Well, first we've got to figure out when the ball hits the ground. And the ball hits the ground after it's fallen how far? When it's fallen 450, because it's being dropped off of a building or something from 450 meters above. We need to solve this for t, and we get 9.583 seconds. Now it asks how fast is the ball traveling when that hits the ground, so we need the velocity at 9.583 seconds. And our velocity equation we found earlier was 9.8a. So if I plug in that 9.583, I get a velocity of 93.913, and it's velocity, so that's going to be measured in meters per second. Now finally, I'll show you one of these. I'm going to give you time to work on the rest. It says temperature readings in degrees Celsius were recorded every hour starting at midnight. The time X is measured in hours past midnight. The data is in the following table. So, midnight to 3 a.m. would be from the point at 0 to the point at 3. At 0, it's 6.5. At 3, it's 4.9. And you're going to find the slope between those. Same thing for 6 and 9. Find their y values. And because it's average, that again means slope. So find the slope. Now this last one says, estimate the instantaneous rate of change at 10. We're estimating, which means we're not going to be exact, but we're going to do our best. So here is 10. In order to best estimate the slope or the velocity at 10, we need to use the point on either side. And our point on either side are 9, 8.3, and 11, 12.1. So when we find slope with that, that'll give us our instantaneous rate of change. Finish these three up. Find their y values, find their slope. We will finish talking about them tomorrow in class.